When it comes to accounting for work mathematically within your energy calculations, we should start with just the basics. So don't forget that your gravitational potential energy, your kinetic, your elastic potential, they can all be calculated using the equations discussed in class. And the new equation is the equation for work. So we know work has occurred when there's a force, any force. It's usually friction in a lot of the examples we look at. But anytime any force acts on the object over a given amount of displacement, and as long as that angle between those two is not 90 degrees, these two cannot be perpendicular. As long as those conditions are met, then the amount of these three that you have will change because work is being performed. You have energy increasing or decreasing among these three forms. So my recommended method of analysis, anytime you have one of these problems, would be to choose two locations for comparison. And ideally, well, not ideally, you need to have one of those two locations have enough information that we can actually calculate the total mechanical energy that we have. And then we know that the second location is going to have that same amount. The new step would be to determine if between those 2 points, whether or not work occurs. And then once you've made those two steps, and I'll show you the small adjustment you can make once you've determined whether or not work occurs, then you solve for whatever you're missing, whether it be velocity, the height of an object, the spring compression, so on and so forth. So as an example, let's say we had a starting point, and the question asked, like, what is the velocity at A and what is the velocity at B? Well, a starting point would probably be good. Provided we have enough information, we could calculate the EPE in the spring, and there's nothing else in the ball. So whatever EPE I have in the spring is eventually going to become the kinetic energy at A. Likewise, that energy will be related to the energy at B. However, there is some work occurring here if we assume that there's friction, so we have to account for that when we analyze B. But none of that happens from the start to point A, so I would not have to worry about that. So let me show you exactly what we're talking about without any values. If I wanted to know how fast the object is traveling at A, I would choose two locations. I think my starting point is a good location, and I think that A is obviously a good location because that's what we're trying to find. So in this case, I have to realize that between my starting point and A, no work occurs because I don't have any friction, I don't have any outside forces coming in and giving a burst of energy to this object. So keeping that in mind, I just use the equation I've always used. I total up my GPE, my KE, and my EPE at the starting point. I total up my GPE, my KE, and my EPE at point A, and I know that the law of conservation of energy says that those two must be equal as long as no work occurred, which we know it didn't because the friction is over here, it's not between star and A. If, however, I wanted to analyze point B, I have to realize that there is work occurring due to this friction here. All right, it's going to act with a force that's leftward as the object moves rightward. So I have to account for the fact that there will be a change in energy. That friction is going to convert some of that energy into heat or sound or other forms that I can't use. So if I'm looking at my start point and point B, I have to realize there is work occurring. Now the only difference is I use this base equation, but I just have to add work to my starting location. If you were to read this like a sentence, you're basically saying the energy or the mechanical energy that I start with, plus whatever work occurs, whether that's positive or negative work, whether that's increasing or decreasing, whatever I start with plus the work that occurred has to equal whatever I had at the end. So the basic rundown is if there is no work occurring between the two locations you've chosen, you just use our base equation. GPE plus KE plus EPE equals GPE plus KE plus EPE. The only difference if you determine that there is work occurring between your two locations is to add work on the side, what I would call the before side. The before and after, start and point A or start and point B, I'm going to add it to the starting side. Let's look at a quick example so you can understand exactly what I mean here. So let's say we have a similar situation, and I say I want to find the velocity of this object at A. Well, I'm given my K value, I'm given how far the spring compressed. We can assume that this ball is at 0. So no work occurs because there's no friction, there's no outside forces. This is a very straightforward energy problem. So I write out my GPE plus KE plus EPE on one side, then on the other. I know those two have to be equal. If I view the starting point, at the start I have no height, I have no velocity, I only have the energy in the spring. At point A, I don't have height, the spring is uncompressed, I only have the kinetic energy of the ball. If I simplify everything, I basically find out that the elastic potential energy at the start here has to equal the kinetic energy at point A. If I plug in the actual equations and then eventually the variables, the only unknown in this equation is the velocity at A, and then I can therefore calculate it. Nice and straightforward. What I'd like you to focus on is that I don't have to incorporate work because no work occurs. It's just like every other problem we've looked at. What happens if, however, I take the same exact problem with the same values, and now I put in a 10-meter stretch of friction that happens to act with 2 newtons over this course in between the starting point and A. Now I have to acknowledge that work does occur because there is an outside force that's now going to affect the motion and therefore the energies of this ball. So again, I'll choose the start point and point A, but since I know work occurs, I must include the plus work on the starting side of my equation. Then I simply go through, I eliminate any energies I don't have, and the simplified version is that rather than just EPE equals KE, it's the starting elastic potential energy plus the new work that I now have to account for, and that's going to equal the kinetic energy at A. So once again, I'll plug in the actual equations I have, the new equation, of course, being F delta X times the cosine of the angle between these two variables, and then plug in everything I know. So I know the mass, and I know the spring constant, and I know the compression of the spring. I know the work because the 2 newtons of friction acts over 10 meters, and I use 180 because the ball is moving or displacing to the right, but the friction acts opposite, which would be to the left. And that would have to equal my 1/2 times the unknown, 1/2 times the mass times the unknown velocity. As we can see here, it's a slightly more complicated equation because I had to account for the work. However, I can now solve for velocity and find that it's about 1.87 meters per second. And that makes complete sense because when I had no friction and the energy was maintained or conserved entirely, that object was traveling faster. As soon as I incorporated some friction, which would perform work and would convert some of that energy into heat or sound, I no longer was traveling at 2.74, I was traveling at a slower 1.87. And that's because this work that we now accounted for came in and took some of that energy away.